The universe is breaking its own rules. We thought we understood the force that holds everything together. For centuries, that was the idea. But now, there are these anomalies out in deep space, and they're forcing physicists to rethink gravity, the laws themselves. Our fundamental picture of reality is being taken apart and rebuilt. Entire galaxies are spinning too fast. It's as if an invisible hand is gripping them, and then there's this other thing. The universe is flying apart. Faster and faster. Some mysterious push is causing it. The answers to these questions, they're rewriting our cosmic story. You're watching the foundations of science shake. An apple falls from a tree. It's pulled toward the earth. That motion is so ordinary it defines our world. For centuries, that simple act was a universal truth. A force of attraction governing the cosmos. Isaac Newton gave it a name, he gave it a law. He described how every object in the universe pulls on every other object. From a falling fruit to a distant moon, his mathematics were powerful. They could predict the motion of planets with stunning precision. And for a long time, that seemed to be the final word. But then came Albert Einstein. He looked at the universe and saw something more profound. He proposed that gravity wasn't a force at all, not in the traditional sense. It was the result of a deeper reality. In his theory of general relativity, massive objects don't pull on things, stars and planets. They warp the fabric of space and time around them. Picture a heavy ball on a stretched rubber sheet. The ball creates a deep well. A smaller marble rolling nearby will curve into that well. It traces an orbit. That's Einstein's universe. Space is the sheet. Mass creates the curves, and we experience those curves as gravity. This geometric idea predicted things Newton couldn't. The precise bending of starlight around the sun, which was later confirmed. It became the unshakable pillar of modern physics, the framework for understanding everything. From black holes to the expansion of the cosmos, the theory was elegant, it was successful. Einstein himself could joke about its dominance. He once said, "Gravity cannot be held responsible for people falling in love." A humorous way to say the concept had transcended science. It became a metaphor, an irresistible pull, a fundamental truth woven into the logic of reality. For decades, every observation fell into line. The orbit of Mercury, signals from distant pulsars, they all matched general relativity's predictions. It was the bedrock, the rulebook of the cosmos, and it left no room for error, which is precisely why the cracks that began to appear were so deeply unsettling. That elegant rulebook, though, it was missing pages. There was a mystery right there, hiding in plain sight. You could see it in the night sky in the shape of those spiral galaxies. Our own Milky Way, for instance, it's this huge pinwheel of stars, billions of them, swirling around a bright center. A dance, really, choreographed by gravity. And for the longest time, the steps seemed obvious. The laws said that stars out on the edges, far from the dense core, they should be moving slower. They're in a weaker gravitational grip, like a planet way out in the solar system, and the stars closer to the center, caught in a much stronger pull, they should be whipping around fast. That was the prediction, a clear gradient from fast inside to slow outside. But then astronomers measured it. They measured the actual rotation, and what they found made no sense. The stars on the outer edges weren't lagging behind. They were moving just as fast as the stars near the center. The whole galaxy, from the bright heart all the way out to the faint spiral arms, was spinning like a solid plate. A rigid disk. That was impossible. Because all the visible matter, all the stars and gas we could see, it just didn't add up. It didn't exert enough gravity to hold onto those speeding outer stars. At the speeds we saw, the galaxies should have been flying apart. The outer stars should have been flung away. Yet they were stable, they were intact. Something else was there, something unseen, providing an immense amount of extra gravity, a kind of cosmic glue holding it all together. This discrepancy, it's called the galaxy rotation problem. And it was brought into focus by the work of Vera Rubin in the 1970s. Her observations of spiral galaxies, they were meticulous. They gave undeniable evidence. The data was clear, and it was consistent across many different galaxies. The math of gravity, it worked so well in our solar system. But on this grand scale, it was failing. It posed a direct question. If our calculations are correct, but the universe disagrees, then what are we missing? What invisible hand is gripping these stars, forcing them to orbit at impossible speeds? This wasn't a small error. It was a fundamental crack in our understanding, a crack in how mass governs motion. And the answer, when it began to take shape, would point to something else. A shadow component of the universe, exerting its pull without ever showing its face. The math just wouldn't work out unless you added something new, a kind of cosmic stuff we can't see or touch. They called it dark matter. It's not evil, it's more like the invisible framework. It holds everything up. It has mass, so it has gravity, but it's dark. It doesn't interact with light. It doesn't shine or glow. It's completely transparent. We only know it's there because of what it does to the things we can see. It's like being in a forest on a still day. You can't see the wind, but you watch the treetops moving together. You hear the leaves, you feel the air get cooler. You know something's there, moving through, something invisible. That's how we find dark matter. We see its gravity at work. We see it bending light from faraway galaxies. That's gravitational lensing. We see it holding galaxy clusters together. And most of all, we see it gripping those outer stars in spiral galaxies, making them orbit so fast. The main idea is that dark matter forms these huge, faint clouds. Halos, they surround every galaxy. Our Milky Way is inside a giant sphere of this unseen material. A sphere that goes way past the last star we can see. The stars we see are like glitter on the surface of a dark pond. The bright galaxy is just the center of something much bigger and heavier. This dark matter halo gives the extra gravity. It makes a deeper, wider well in space than the visible stuff could make alone. So when a star on the edge orbits, it's feeling the pull from all this invisible mass. That's why it can move so fast and not fly off. For decades, this idea saved the Standard Model. It fixed the galaxy rotation problem, but it did more than that. When they looked at the afterglow of the Big Bang, the cosmic microwave background, the patterns only made sense if dark matter was there from the start. It helped explain how galaxies formed so fast. Dark matter became more than a fix. It became a foundation, a pillar of the whole cosmic story. We built our best model of the universe on it. The assumption is that this invisible stuff is about 85% of all matter. We've been living in a cosmos ruled by a ghost we've never seen. We were looking for ghosts in the distant galaxies, but a mystery was brewing much closer to home, with two robotic explorers, Pioneer 10 and Pioneer 11. They were launched in the early 70s. Their missions were triumphs, the first to fly by Jupiter and Saturn. They sent back images of swirling storms and icy rings. And after those encounters, they just kept going, sailing out past Neptune, into the deep, quiet dark of the outer solar system. They became our most distant emissaries. And as they drifted farther out, scientists tracked them with incredible precision. They listened for their faint radio signals. They timed how long those signals took to get back to Earth. This data painted a picture of their trajectory, or so they thought. Because the pioneers weren't quite where they were supposed to be, there was a tiny, persistent drift. An almost imperceptible tug, pulling them back toward the sun, an acceleration so small, about 10 billion times weaker than gravity here on Earth, but it was constant. And it was unexplained. According to Newton and Einstein, once you're that far out, the sun's gravity is the dominant force, and its pull weakens with distance. The pioneers should have been slowing down in a very predictable way, but they were slowing down a tiny bit more. It was as if an extra, unseen hand was gently applying the brakes. This was the Pioneer Anomaly, and it was measured right here in our own cosmic neighborhood. This wasn't about distant galaxies or hypothetical dark matter. This was a precise experiment, happening in real time with hardware we built, and the math was off. For years, a small team worked to solve it. They considered every possible explanation. Could it be the gentle push of heat? The spacecraft's nuclear power sources gave off warmth. Photons carrying that heat could provide a tiny thrust. They built intricate thermal models of the entire spacecraft. They checked for minute fuel leaks from long dormant thrusters. They looked at the pressure of the solar wind, the gravitational pull of the Kuiper belt. They chased down every lead, and one by one they ruled them out. The drift remained, a stubborn, quiet signal in the data that refused to go away, and this posed a question. A deeply unsettling one. If our fundamental laws of gravity can't fully account for the motion of a probe in our own solar system, how can we trust them to describe the universe at large? The anomalies suggested the problem might not be out there with missing matter. It might be right here, in the law itself. The Pioneer drift became a crucial clue. A whisper from the void, that perhaps gravity behaves differently over vast, empty distances than our equations predict. The Pioneer probes were drifting off course. And there was another signal. Another strange reading in the data, this time from missions much closer to home. It's called the Fly-By Anomaly. It happens during a gravitational slingshot. That's a very precise maneuver. A spacecraft swings by a planet, and it steals a little bit of that planet's orbital energy to speed itself up. It's a well-understood trick. The physics is exquisite. Engineers can predict the exact speed boost, down to a fraction of a millimeter per second. It's a reliable tool. It's how we send probes to the outer planets. But then the numbers started whispering. Missions like Galileo heading to Jupiter and Rosetta going to a comet. They did these Earth flybys. They'd whip around our planet and race away. And ground teams would track their velocity with incredible precision. Every time, the probes came out a little faster than they should have. The difference was minuscule. Just a few millimeters per second. In the grand scheme, for a mission traveling tens of thousands of kilometers an hour, it was almost nothing. But in orbital mechanics, where predictions are perfect, it was everything. It was a consistent nudge, an unexpected push at the bottom of the hill, and it happened again and again across multiple spacecraft. The engineers, the masters of this celestial calculus, were baffled. They checked their models, they rechecked them. They accounted for the atmosphere, the magnetic field, the tidal pull of the moon. Nothing explained the extra speed. This wasn't a problem of missing matter like with the galaxies. This was a problem with the force itself, in a very specific, high-precision scenario. It suggested gravity's influence might not be perfectly uniform. That under certain conditions, maybe when an object is moving in a particular way relative to a planet's spin, the rules might have a subtle clause. A hidden clause we haven't read. The Fly-By Anomaly is a fingerprint, a tiny, almost imperceptible smudge on the lens. It tells us that even in our own backyard, with missions we built and trajectories we plotted, the universe is still holding something back. These three clues, the spinning galaxies, the drifting pioneers, the overachieving flybys, they point in the same direction. Our map of gravity, for all its elegance, might be incomplete. And when the map is wrong, you have to question the ground, the very ground you thought you were standing on. But a powerful idea, once it gets in, it's hard to get out. Dark matter became the main story, the invisible structure for everything, but then our tools got better, and the story itself started to have holes. The ghost wasn't acting the way it was supposed to. When astrophysicists run these universe simulations, they put in the laws of physics. They put dark matter in as a main part. Those simulations should make galaxies that look like the ones we see. And on the big scale, they do. The cosmic web, the filaments and voids, it all matches. But when you zoom in on a single galaxy, the simulation and the real thing don't line up. The problems have names. There's the too big to fail problem. In the simulations, our Milky Way should have hundreds of small, dense satellite galaxies around it. each held by its own dark matter halo. They should be too heavy, too bound by gravity, to just fall apart. But we only see a few dozen, and they're fainter, much less dense than the simulation says. Where are all those galaxies that should be there? Then there's the cusp core problem. The simulations say dark matter should pile up in a sharp peak, a dense cusp, right in the center of every galaxy. But when we look at the actual motion of stars and gas in the centers of small galaxies, we see something else. We see a soft core, like something smoothed out that central peak. These aren't small issues, they're persistent mismatches between our best models and the real universe. They suggest dark matter, if it's there, might not be as simple or as cold as we thought for decades. And then, in labs deep underground, physicists built these exquisite traps. Vats of liquid xenon, crystals kept almost at absolute zero. They wait in silence, shielded, listening for the faintest whisper, for a dark matter particle to finally bump into normal matter. Decades have gone by. The detectors are orders of magnitude more sensitive, and the silence is profound. The main candidate particles haven't shown up. That absence is its own kind of data, a growing quiet. So now some prominent voices in physics are asking a different question. What if we've been reading the clues wrong all along? The astronomer Vera Rubin, whose work really made the case for dark matter, she said something once. She said, if she could choose, she'd rather learn that Newton's laws need to be modified to describe gravity over large distances. That was more appealing than a universe filled with a new kind of particle. Her words point to a crossroads. There are two paths. One says the universe is full of invisible stuff we can't find. The other says maybe our understanding of the visible force, gravity itself, is incomplete. That the flaw isn't in the map of matter, but in the map of the force. And this is where science does its real work. Not by holding onto an idea, but by testing it to its limit. And when the inconsistencies pile up, it has to have the courage to look somewhere else. To ask if the rules themselves need to be rewritten. The silence from the detectors just kept growing, and in that quiet, a different answer started to form. It began with one question: what if there's no ghost? What if the problem isn't missing matter but the force itself? That's the idea behind modified Newtonian dynamics. MOND, a physicist named Mordechai Milgram, proposed it in the early 80s. His premise was simple. Maybe Newton's second law, the link between force and acceleration, isn't universal. Maybe it changes when gravity gets very, very faint. Think of water. Normally it flows like a liquid, but at extremely low temperatures it shifts. It can become a superfluid. MOND suggests something similar for motion under gravity. In our everyday world where gravity is strong, Newton and Einstein work perfectly. But out at the edge of a galaxy, the pull from the core is a billion times weaker than what we feel here. The rules might change there. Acceleration might not respond to force in the same linear way. Milgram proposed a specific threshold, a tiny, almost imperceptible acceleration. Below that line, the old equation gets a gentle modification. The change is small, but the consequence is enormous, because when you apply this tweaked law to a spiral galaxy, the math naturally produces a flat rotation curve. Those outer stars, moving just as fast as the inner ones, they're no longer a problem for an invisible halo. They're the direct prediction of the revised law. The galaxy rotation problem, the thing that launched the search for dark matter, it just disappears. It emerges from the math. For its proponents, that's the elegance of MOND. It solves the central mystery without adding a single new particle. It uses only the stuff we can see. And early on, it did something even more compelling. It made predictions. Before new data came in, MOND calculated what certain galaxy rotation speeds should be. And when astronomers looked, the observations matched. Not just roughly, but with a precision that surprised people. Stacy McGaugh, an astrophysicist, has often noted this predictive power. He describes a spooky alignment, where the universe seems to follow this modified rulebook with eerie consistency. For its champions, MOND isn't just a patch. It's a more parsimonious explanation. A universe that needs no mysterious substance, just a slight correction to how the visible substance moves. It's the most direct challenge to the gravitational status quo we have. A call to rewrite the fundamental laws, not to populate the cosmos with ghosts. But rewriting a law that's held for centuries is no small thing. It demands more than solving one puzzle. It has to explain everything else, too. MOND elegance is hard to ignore. You have this one stubborn problem: the way galaxies rotate. And MOND makes it a simple prediction. For certain galaxies, especially the faint, diffuse ones, the fit is astonishing. It matches the speeds of stars and gas with a precision that dark matter models often struggle to reach. That's its great strength. It feels like a direct conversation, using only the visible matter as a guide. Proponents see a fundamental simplicity there. A universe that doesn't need an invisible scaffold, just a slight recalibration of how motion works under extremely weak gravity. The theory has evolved, too, into more formal frameworks like TVS, trying to build a relativistic version that could compete with Einstein's work on all fronts. But for all that beauty in explaining galaxy rotations, the theory faces monumental hurdles elsewhere. The biggest one is gravitational lensing. We see it clearly. A galaxy cluster's immense gravity bends light from galaxies behind it, creating arcs and rings, a cosmic magnifying glass. The amount of bending tells us the cluster's total mass. And according to the light we see from stars and hot gas, there isn't nearly enough visible mass to cause that distortion. Dark matter explains this seamlessly. Its invisible halo adds the needed heft. MOND, in its original form, struggles. It was designed for the slow, weak accelerations within a single galaxy, not the fierce gravity of a dense cluster. To match the lensing we see, most MOND-inspired models still require some additional, unseen mass. They often call it hot dark matter or something similar. To critics, that sounds suspiciously like the very thing the theory sought to eliminate. Then there's the large-scale structure of the universe, the cosmic web of filaments and voids shown in galaxy surveys. It formed through gravity pulling matter together over billions of years. Computer simulations that include cold dark matter reproduce this web with stunning accuracy. They show how tiny ripples in the early universe could grow into the structures we see. A pure MOND universe without any form of unseen matter has a harder time building this cosmic architecture so quickly. So the debate isn't settled. It's a heated, living conversation. One side points to the exquisite fits in galaxy dynamics and asks why we would invent a universe full of ghosts to avoid tweaking a law. The other side points to the bulletproof evidence from lensing and the cosmic microwave background and asks why we would abandon a framework that explains so much, just because we haven't caught one specific particle yet. Where does that leave us? With a profound stalemate. Dark matter has a coherence problem. It works magnificently on the largest scales but gets messy and unpredictable within individual galaxies. MOND has a completeness problem. It solves the galactic mystery with grace but stumbles when asked to explain the rest of the cosmos. This isn't a weakness of science. It's its strength. We have two competing maps, and each one fails to chart a different part of the territory. That tension is a signal. A loud, clear signal that we are missing a fundamental piece. Maybe the final answer isn't a simple choice between them, but a synthesis. A new law of gravity that incorporates the insights of both, revealing a deeper truth about the fabric of reality. The very fact that we have two compelling, yet incomplete, paths forward tells us the mystery is real, and the discovery waiting for us will be revolutionary. The debate about galaxies is one thing, but the universe itself has its own story, a story about its own fate. For most of the 20th century, we knew the universe was expanding. We saw the galaxies all flying apart, like dots on an inflating balloon, and the logical question was, what happens next? Does gravity pull it all back together into a big crunch, or does it just keep expanding forever? slowing down until it coasts to a stop. The assumption was that gravity would act as a brake. The expansion should be slowing down. That was the only sensible outcome. Then, in the late 90s, two teams set out to measure this slowdown. They used a specific kind of stellar explosion, a Type 1, a supernova, as a cosmic yardstick. These explosions have a known brightness, so by measuring how dim they looked in very distant galaxies, they could calculate how far away they were, and how much the universe had stretched since that light left. They were looking for the sign of a slowdown. What they found instead sent a shockwave through physics. The most distant supernovas were fainter than they should have been. The universe wasn't slowing down, it was speeding up. The expansion was accelerating. This was so unexpected, so contrary to all intuition, that the leaders of both teams won the Nobel Prize. The finding was undeniable. Some mysterious pressure was overcoming the collective gravity of everything. Every star, every galaxy, every particle of dark matter, and pushing the cosmos apart faster and faster. To explain this, cosmologists invoked a new concept. Dark energy. Think of it as the opposite of gravity, a kind of anti-gravity woven into the fabric of empty space itself. If dark matter is the invisible glue holding galaxies together, dark energy is the invisible force tearing the cosmos apart. On the grandest scale, the numbers are staggering. Our best measurements say everything we see and know. All the planets, stars, galaxies, even the dark matter. It makes up only about 5% of the universe. Dark matter is about 27%. And dark energy, it constitutes a dominant 68% of the total energy of the cosmos. We are living in a universe dominated by something that pushes. A simple analogy helps. Picture a loaf of raisin bread baking. The dough is the fabric of space. The raisins are galaxies. As the dough rises, all the raisins move apart. That's the normal expansion. But now imagine the yeast in the dough suddenly becomes more potent. The dough doesn't just rise, it inflates at an ever-increasing rate. The raisins fly apart faster and faster. That's our accelerating universe, with dark energy acting as that mysterious, potent yeast. This discovery forces a parallel question. Is dark energy a real, new component of the universe? Or is it a monumental clue that Einstein's theory of gravity breaks down? Not just within galaxies, but on the scale of the entire cosmos. Could the accelerating expansion be a sign that our equations for gravity on cosmic scales are simply wrong? That what we call dark energy is just the gap between our flawed theory and reality. This anomaly elevates the crisis from the motion of stars to the ultimate fate of everything. It connects the strange behavior of galaxies to the very geometry and destiny of spacetime. We are left with a cosmos where 95% of its content is fundamentally unknown to us. And the force we thought we understood might be playing by a different rulebook. At every scale, the search for answers is no longer about fixing a model. It's about rediscovering the universe from its foundations. That cosmic acceleration means we have to rethink things completely. If dark energy isn't some new substance, then the equations themselves have to change. That's the frontier now, modified gravity. It's not about adding new particles to the universe. It's about rewriting the foundational script, how space and time and matter interact. They're building new mathematical languages to describe what we see. One path is called f of r gravity. In Einstein's theory, there's a key term for the curvature of spacetime, the Ricci scalar. It's a single number that captures how warped space is at any point. In f of r gravity, that simple term gets replaced by a function, a more complex mathematical expression. Think of it like upgrading a basic volume knob to a full graphic equalizer. Instead of one control for curvature, you have a range of adjustments. And these adjustments can be tuned so gravity behaves exactly as Einstein predicted here in the solar system. But on the vast, empty scales between galaxies, the equations shift. The modified law can naturally produce an accelerating expansion. No dark energy needed. The emptiness itself, the low density of the cosmos, triggers a change in how gravity works. Another idea comes from scalar tensor theories like the Brans-Dicke model. Here, gravity isn't described by the geometry of space alone. There's an additional, invisible field that permeates everything, a scalar field. You can picture it as a kind of cosmic weather. A new layer of reality that interacts with matter and shape. In this view, the strength of gravity isn't a constant. It's not a fixed number in the equations. It's a variable set by this background field. And that field can change over cosmic time and distance. It's as if the pull of gravity has a dimmer switch, and the expansion of the universe is slowly turning that dial. These theories propose a dynamic conversation between the shape of space and this new field. A conversation that could mimic the effects of both dark matter and dark energy from a single, deeper principle. What unites these approaches is a bold proposition. Gravity isn't one simple force with one set of rules. It may be an emergent phenomenon, a consequence of a more complex reality that shows different faces in different environments. Near a black hole in that high-gravity realm, it acts one way. In the crowded disk of a galaxy, perhaps another. And in the near vacuum between galaxy clusters, it shifts again. The anomalies we see, from galaxy rotation to cosmic acceleration, could be different signatures of this same multifaceted behavior. This is the cutting edge. It's not about discarding Einstein. It's about extending his genius into realms he never could have tested. It's an active construction site. The blueprints for reality are being redrawn, equation by equation, prediction by prediction. The goal is a single, unified framework, where the invisible hand and the accelerating push aren't mysterious substances. They're natural outcomes of a richer law of gravity. Rewriting the laws of physics is one thing. Proving them is something else entirely. In a normal lab, you control things, you run the experiment again. But cosmology's lab is the whole observable universe, and the experiments are observations. Observations of ancient light. We can't make a new cosmos. We can't adjust gravity and watch a galaxy form. All we can do is look out, look with more and more precision, and ask the universe to show us through the patterns it left behind. That's the challenge here. We're detectives, and the crime scene is the entire sky, billions of light years across. It happened once, so the tools matter. This new generation of tools, it's revolutionary. We're entering a golden age of data. The Euclid Space Telescope from Europe. Its mission is to make a map. The most detailed 3D map of the universe ever. It will chart billions of galaxies across 10 billion years of history by seeing how they cluster, how their light gets bent by invisible matter. Euclid will weigh the dark universe. It will trace dark matter. It will measure the push of dark energy. Then there's the James Webb Telescope. It looks back to the infancy of galaxies. It sees the first structures forming, clues about how dark matter guided that. And from the ground, the Vera Rubin Observatory. It will scan the whole southern sky every few nights. It will watch for changes, catalog billions of objects, catch cosmic events. The data will be a flood, a torrent of starlight to decode. The analysis is painstaking. It's searching for tiny signals in the noise. The slight warping of galaxy shapes weak lensing that tells us about mass. The precise distances to millions of galaxies that reveal how the cosmos expanded. The way galaxies cluster, testing the gravity that pulled them together. Each measurement is a vote for or against our current models. And as this data arrives, it puts pressure on both ideas. The modified gravity theories, they make predictions about how structure should grow, how light should bend, predictions that often differ from the dark matter story. The maps from Euclid and Rubin, they'll see those differences. So the question is in the data. Will the universe follow a simpler law, one that uses only the matter we can see? Or will it show the scaffolding of dark matter, the smooth influence of dark energy, so clearly that no alternative is left? The answer is in the light. In the work of turning starlight into understanding, We're building a better map, not of territories but of the forces that carve them. And in the patterns of billions of distant suns, the universe is about to cast its vote. The Hubble tension, it's a crisis over a single number, the Hubble constant. It tells you how fast a galaxy is moving away from us for every megaparsec of distance. It's the expansion rate of the universe right now, and we have two incredibly precise ways to measure it. But they give two different answers, and the gap between them won't go away. One method looks back to the infant universe, to the cosmic microwave background, that faint afterglow from when the cosmos was just 380,000 years old. By mapping its tiny temperature fluctuations, missions like Planck can deduce the ingredients of the early cosmos, the amounts of ordinary matter, dark energy. You take those ingredients, plug them into our standard model of cosmology, and run the simulation forward for 13.8 billion years. It predicts what the expansion rate should be today. That's a prediction from the beginning of time. The other method measures the present directly. Astronomers use the cosmic distance ladder. They start with nearby stars, where we can measure distance with geometry. They use those to calibrate the true brightness of more distant objects, Cepheid variable stars, Type 1 supernovas. By measuring how fast those distant beacons are moving away and how far away they truly are, you get a direct, local measurement of the current expansion rate. That's an observation from the here and now. Both methods are monuments to human precision, and they are stubbornly in conflict. The early universe prediction gives a lower number. The local measurement gives a higher one. The discrepancy is about 9%. That might sound small, but in cosmology, it's a chasm. The error bars on each measurement have shrunk with better data. And the gap remains. It's persisted for over a decade. This isn't a mistake, it's a message. The Hubble tension suggests a fundamental flaw in our story. Either our understanding of the early universe, encoded in that cosmic microwave background, is wrong, or our understanding of how the universe evolved from then to now is wrong. Maybe there was an unknown episode of physics in the first moments, a brief burst of something that changed the initial conditions, or it points back to gravity. Maybe the laws governing dark energy, or how dark matter clumps, are subtly different than our equations say. Maybe the force driving the expansion has evolved in a way our models don't capture. This tension is more than a puzzle. It's a direct observational challenge. Any new theory of gravity, any revised model of the cosmos, has to do one essential thing. It has to explain this number. It has to reconcile the story of the beginning with the reality of the present. The universe is telling us two different tales about its own expansion. Our task is to find the single, deeper story that makes them both true. The answer will rewrite not just a chapter, but the entire book. Temperature is real. But it's not fundamental. You can't look at one molecule and ask for its temperature. That idea only works with a huge collection of particles, all moving together. The heat you feel, the reading on a thermometer, that's a collective property. An illusion that comes out of the chaos of countless tiny parts. So what if gravity is like that? Not a fundamental force in the fabric of space, but a collective illusion. An emergent phenomenon. It's one of the most radical ideas in physics now. It means the pull of a planet, the curve of a star's orbit that might not be the primary reality. It could be a side effect, a consequence of something deeper happening at the quantum level. Theorists like Eric Verland have been working on this view. He says gravity emerges from information, specifically from how quantum information gets entangled across the universe. And that idea borrows from something even stranger, the holographic principle. Back in the 90s, physicists studying black holes found something startling. They realized all the information about what fell into a black hole wasn't lost inside its volume. It was encoded on its two-dimensional surface, the event horizon. The three-dimensional interior, with all its complexity, could be represented perfectly on a two-dimensional boundary. It was as if our three-dimensional reality was a projection. A hologram, a cosmic illusion generated from information written on a distant screen. Verlin's emergent gravity takes that further. He suggests space itself is built from a vast network of quantum bits, all entangled. These bits store information, and when you add matter to this system, it disrupts the information structure. It creates an imbalance, and the natural tendency of this quantum network to return to equilibrium, to maximize its disorder, its entropy, that tendency manifests as a force. And that force, coming from the collective behavior of countless quantum entanglements, is what we feel as gravity. In this picture, an apple falls to Earth not because it's pulled by warped spacetime, but because the quantum information linked to the apple and the Earth interact in a way that drives the whole system toward higher entropy. It's a statistical push, not a geometric pull. The promise here is huge. This framework tries to derive the laws of gravity, Newton's, Einstein's, from the first principles of quantum information and thermodynamics. But maybe its most compelling test is with the anomalies. Verlin's calculations show that in regions of extremely low gravity, like the outer edges of galaxies, this emergent force naturally changes. It produces an extra component, an apparent additional attraction without needing any invisible matter. In his theory, what we call dark matter isn't a particle. It's a signature, a fingerprint left by the way quantum information is structured in the cosmos. The mismatch in galaxy rotations, the Pioneer Anomaly, they could all be different facets of this single, deeper principle. This perspective turns our intuition inside out. Gravity is no longer the director of the cosmic play, telling matter how to move. Instead, it's an understudy that only appears when the lead actors, quantum information and entropy, do their dance. It suggests the deepest layer of reality isn't force or matter, but information. A universe that computes itself into existence. It's still highly theoretical, debated. But emergent gravity represents a profound shift. It asks us to consider that the most familiar force in our daily lives might be the ultimate cosmic illusion, a ghost in the machine of quantum data. That idea of an emergent universe built from information, it brings us to the heart of the storm, the greatest unsolved problem in physics, the ultimate clash of titans. On one side, general relativity, Einstein's masterpiece. It describes the cosmos with breathtaking elegance, the dance of planets, the bending of light. The expansion of space itself, it's the theory of the very large. It sees a universe that is smooth, continuous, and deterministic. A cosmic stage, matter tells spacetime how to curve. And curved spacetime tells matter how to move. On the other side, quantum mechanics, the rulebook for the subatomic realm. It governs particles and forces at the smallest imaginable scales. In that world, nothing is certain. Reality is a game of probabilities. Particles can be in two places at once. They can tunnel through barriers. They're connected by spooky action at a distance. The quantum world is grainy, fuzzy, and fundamentally unpredictable. It's the theory of the very small, and here is the crisis. These two theories, each spectacularly successful in its own domain. They are mathematically and philosophically incompatible. They speak different languages. They describe different realities. When you try to combine them, to apply quantum rules to the gravitational field, the equations break down. They produce infinities, nonsense answers. It's like trying to mix oil and water. A conceptual mess. This incompatibility suggests our understanding of gravity is incomplete. That Einstein's smooth fabric of spacetime must give way to something else. Theorists call this the Planck scale, a distance so unimaginably tiny, a billionth of a trillionth of a trillionth of a centimeter. At that scale, the universe might not be smooth at all. It could be a seething, chaotic froth, a quantum foam, where tiny wormholes blink in and out of existence. Where space and time themselves lose their meaning. In this realm, the very concepts of here and now dissolve into probability. Stephen Hawking spent much of his career wrestling with this. His work on black hole radiation showed that gravity and quantum mechanics must talk to each other, that a theory of quantum gravity is not a luxury. It is a necessity. He believed the key to unifying physics would be found where these two worlds collide, at the singularity inside a black hole, or in the first instant of the Big Bang. So let's return to our deep space anomalies, the galaxies spinning too fast, the universe accelerating apart. What if these aren't just puzzles about missing matter or a modified force? What if they are macroscopic fingerprints of this deepest disconnect? The clues we see across billions of light years might be echoes of that quantum foam. Manifestations of physics playing out on a scale we cannot yet see. Could the strange gravitational effects we attribute to dark matter actually be the large-scale consequence of quantum entanglement? As emergent gravity suggests, could the push of dark energy be a signal that the vacuum of space itself has a complex quantum structure, one that subtly alters the expansion? The anomalies force us to ask if the rules change not just with distance, but with scale. If the universe operates with one set of instructions for stars and galaxies and another, more fundamental set for the quantum bits that underpin everything. This frames our search in a new light. We are not just looking for a new particle or tweaking an equation. We are hunting for the bridge, the theory of everything. A single framework that can describe the gravitational sway of a galaxy and the probabilistic jump of an electron. The anomalies in deep space, these cosmic discrepancies. They might be the very signposts pointing toward that bridge. They are the universe's way of showing us where our current maps end, and where the true, unified territory of reality begins. There's a real comfort in looking back, because this has all happened before. At the end of the 1800s, a lot of the top physicists thought the big work was finished. The laws of motion, thermodynamics, electromagnetism, it felt like they explained everything. Lord Kelvin, a huge figure back then, he famously said there were only two small clouds on the horizon. The rest was clear sky. He was talking about two little anomalies, things that the beautiful, complete structure of classical physics couldn't quite solve. And those two small clouds, of course, they turned into thunderstorms. They became the twin revolutions of the 20th century, relativity and quantum mechanics. They didn't just add to the old physics, they rewrote it completely. They showed that our gut feeling about space and time and matter, it was just an approximation. A useful story, but for a limited world. One of those clouds had a name, the precession of Mercury's orbit. Mercury, the closest planet to the Sun, it doesn't trace the same perfect ellipse every year. The point where it's closest to the Sun, it's perihelion, it drifts. It slowly advances. Newton's laws, using the gravity of the Sun and the known planets, they could explain most of that drift. But not all of it. There was a tiny piece left over, a discrepancy of just 43 arcseconds per century. To picture that, it's like the width of a human hair seen from 10 meters away. An almost invisible wobble. For decades, astronomers tried to explain it. Maybe there was an unseen planet, Vulcan, orbiting inside Mercury's path. They looked and found nothing. The wobble stayed, a stubborn, quiet signal in the data. Then Einstein came along. His new theory of gravity, general relativity, it wasn't built to solve this problem. It came from a deep rethinking of space and time themselves. But when he applied his equations to Mercury's orbit, something happened. The math just produced that exact 43 arcseconds. No extra planets, no fudged numbers. The wobble came right out of the geometry of a sun-warped spacetime. It was a perfect prediction. That tiny anomaly became one of the first big validations of a theory that would reshape everything. The parallel to now is striking. Today's deep space anomalies, there are modern Mercury wobbles, the galaxy rotation problem, the cosmic acceleration, the Hubble tension. They're the small clouds on our 21st century horizon. They're gaps between our beautiful, established models and the stubborn data from the cosmos. And just like with Mercury, the solutions people are talking about aren't small tweaks. They're revolutions waiting to happen. Dark matter and modified gravity, they're not just competing ideas. They're competing visions of reality. Each one asks us to let go of something fundamental we thought we knew. This historical view is crucial. It reframes the current crisis not as a failure of science, but as its greatest strength. Science doesn't move in a straight line, just adding facts. It leaps. It's marked by these times of deep uncertainty, where the old rules start to crack under new evidence. That cracking sound, that's discovery happening. The discomfort we feel, the debate, the lack of a clear answer, that's not a flaw in the system. It's the system working exactly as it should. It's the vibrant, messy, thrilling process of humanity pushing its understanding of the universe forward. We're standing in that moment now, that crackling potential right before the leap. These anomalies go beyond physics. They reach something deeper in us. For centuries, we thought the cosmos ran on fixed, eternal laws. Laws we could find and write down. That belief gave us order. A universe that was, at its heart, knowable. But if gravity isn't a constant, if its rules change with scale and emptiness, then that foundation shakes. We face a humbling truth. Our understanding is provisional. Our maps are always incomplete, and that's not a failure. It's a revelation about the quest itself. The universe isn't a puzzle to be solved. It's a conversation, and we're just learning the language. This rethinking raises profound questions. If the laws of physics aren't absolute but depend on context, what does that say about reality? Is there no single, true description of the cosmos? Only different views at different scales. Some philosophers of science see this as liberation. It moves us from a rigid, clockwork universe to one that's dynamic, relational. Maybe even participatory. Our observations don't just record the cosmos. In some small way, they engage with it. So this crisis in cosmology redefines the scientific method. It shows that science isn't a march toward final answers. It's a continuous process of questioning and adaptation. The method is resilient because it lets its own foundations be tested and rebuilt. And this lofty pursuit has down-to-earth consequences. The drive to test gravity, to track spacecraft across billions of miles, pushes technology. It leads to advances in precision measurement. The atomic clocks used to track those fly-by anomalies are the ancestors of GPS. The deep space networks built to talk to the Pioneer probes evolved into systems that now connect our planet. Modeling complex gravitational interactions drives innovations in computing. Solving the mystery of cosmic acceleration could one day reveal insights about spacetime. Insights that transform how we think about energy or propulsion or the nature of vacuum itself. The quest to understand the force that holds galaxies together spins off technologies that hold our world together. Ultimately, the search is about more than correcting a textbook. It's a search for coherence, for a story that makes sense of the apple falling in a garden and the galaxy spinning in the void. It's about finding our place in a narrative grander and stranger than we imagined. When we look up at the night sky, we're not just looking at points of light. We're looking at a question about the rules of existence, and in trying to answer it, we're also answering a question about ourselves. Who are we in a universe that's still writing its own laws? We are the ones who get to listen. We are the ones who get to ask. And in that asking, we connect our fleeting human experience to the vast, unfolding story of everything. Our future in space, it depends on knowing the rules. Every mission we send out, from a satellite around Earth to a probe heading for Pluto, it all relies on a precise understanding of gravity. It's the map we use. We use it to calculate when to launch, to plot slingshot maneuvers around planets, to aim for a specific point in space years ahead. But if that map has distortions, even subtle ones, those small anomalies like the Pioneer drift or the fly-by mystery, they're more than just curiosities. For a spacecraft on a 10-year journey, a tiny unaccounted-for acceleration could mean missing its target by thousands of kilometers, or flying right past it. And as we look at more ambitious targets going back to Jupiter's moons, a sample return from Venus, a crewed mission to Mars. The precision of our gravity model becomes everything. It's the difference between success and catastrophic failure. So solving these mysteries, it's not just academic. It's an engineering imperative, and a deeper understanding could open up new possibilities for propulsion. For decades, our ideas for reaching other stars have been limited by rocket fuel and the speed of light. But if gravity comes from a deeper quantum reality, like some theories say, it might offer new handles. Could we learn to interact with that underlying structure? The idea is speculative, but history shows that breakthroughs in fundamental physics often lead to technological leaps no one saw coming. Understanding electromagnetism gave us global communication. Grasping nuclear physics gave us new energy. A true theory of quantum gravity, born from solving these cosmic anomalies, might one day suggest ways to mitigate gravity, or even harness it in ways we can't yet conceive. It could change interstellar travel from a millennia-old dream to a project of centuries. This recalibration of gravity, it also reshapes how we search for life. When astronomers find a new exoplanet, one of the first questions is if it could be habitable. Is it in the star's Goldilocks zone, where liquid water is possible? But a planet's climate and long-term stability, they depend on more than distance. They depend on gravity. The star's gravitational pull shapes the planet's orbit. The gravitational interactions with other planets in the system determine whether that orbit stays stable over billions of years, or gets violently perturbed. If our models of how gravity works in complex systems are even slightly off, then our assessments of which exoplanets are stable, Earth-like oases, could be wrong. We might be looking in the wrong places, or misreading the signs we see. So the stakes are both immediate and profound. They connect the most abstract theoretical physics to the most concrete human ambitions. We're a species on the brink of becoming interplanetary, and the very laws we use to navigate that transition are under review. This moment of crisis in cosmology, it's not a sign that science is failing. It's a sign we're pushing against the boundaries of our knowledge because we intend to go beyond them. The anomalies in deep space are like warning buoys on a cosmic ocean. They tell us our current maps aren't sufficient for the voyages we want to make. Charting them correctly is the first, crucial step. The next great journey starts there. The universe isn't letting go. That's the first thing. When physicists talk about rethinking gravity, they're not saying the rules of our everyday world are about to change. The apple still falls, the moon still orbits, spacecraft still follow the curves Newton and Einstein predicted. That part is settled, tested to an extraordinary precision. It works. The rethinking happens at the extremes, in the emptiness between galaxies or the first moments of the cosmos. It's about extending our understanding into realms where our current equations start to whisper they might be incomplete. And this leads to a point of confusion. You might hear dark matter hasn't been found, so it must be a failed idea. Or that MOND solves galaxy rotations, so it must be the new truth. Both miss the mark. They misunderstand how science actually progresses. Science isn't a courtroom. One idea isn't proven guilty and another declared innocent in a single verdict. It's a long, collaborative investigation. Dark matter isn't a single claim, it's a framework, a hypothesis that grew into a robust model because it explains a wide array of phenomena. From the cosmic microwave background to the bending of light in galaxy clusters. The fact we haven't directly detected its specific particle yet is a puzzle within that investigation. Not a dismissal of the entire case. It means we need better detectors, or we need to consider different types of dark matter. On the other side, modified Newtonian dynamics is a brilliant counter-hypothesis. It offers a compelling alternative for one specific set of observations, galaxy rotations, with stunning predictive power. But a hypothesis must explain all the evidence to become a widely accepted theory. And MOND, in its current forms, struggles with the evidence from gravitational lensing and the large-scale structure of the universe, without incorporating some additional elements. So it, too, is a work in progress. Neither side has won, both are being tested. This tension isn't a sign of weakness, it's the engine of discovery. To navigate this, it helps to know what scientists mean by certain words. A scientific law is a concise description of how nature behaves under certain conditions. Newton's law of universal gravitation describes the attractive force between masses. It doesn't explain why that force exists. It just mathematically describes its action with remarkable accuracy. A scientific theory is much broader, a well-substantiated explanation of why and how. Einstein's theory of general relativity doesn't just describe gravity. It explains it as a consequence of the curvature of spacetime. It's built from a mountain of evidence. And it has survived countless attempts to disprove it. A hypothesis is a proposed explanation, a testable starting point. Dark matter and MOND began as hypotheses. They're both being pushed toward the status of a full theory by evidence, and that journey is messy and competitive. Think of it like mapping a new continent. The old maps showed a coastline, but beyond it was just blank space labeled "Here be dragons." Dark matter is like one explorer returning and saying, "The dragons are real." And they are holding up the mountains you see in the distance. We just haven't caught one yet. MOND is like another explorer saying, "There are no dragons." The mountains are held up by a new kind of rock that behaves differently under its own weight. Both explorers are using the same coastline data, but they propose radically different things for the interior. The debate isn't about the coastline, the falling apple, the orbiting moon. It's about what lies in the vast, uncharted territory beyond. And the only way to settle it is to keep exploring. To gather more data from telescopes and experiments. This process, with all its disagreement and uncertainty, isn't science broken. It's science working exactly as it should. It's how we move from the comfort of the known coastline into the uncertain depths of the real cosmos. The search for answers is a global effort. It's not something that happens in one isolated lab. It's a huge network of work, spread across the whole world. You have telescopes in the Atacama Desert in Chile, where the air is thin and dry. They're looking into a clear night sky. And then you have instruments down in Antarctica, on the frozen plateau, studying the ancient light from the Big Bang. There are labs deep underground in Italy, in South Dakota, listening for signs of dark matter. And there are telescopes in space like Euclid and JWST, orbiting silently, mapping the dark universe. Thousands of people are working on this. Physicists, astronomers, engineers, data scientists. They speak dozens of languages, but they're all asking the same question about gravity. A question this big needs collaboration on a massive scale. Take the Event Horizon Telescope. It isn't a single telescope. It's a network of radio observatories scattered across the planet, from Hawaii to the South Pole to the mountains of Spain. They synchronize them using atomic clocks that created a virtual dish, an Earth-sized instrument, powerful enough to finally capture an image, the shadow of a black hole. That picture, the fiery ring around a dark center, that came from years of work. Hundreds of researchers from many different countries. It was the same with the Dark Energy Survey. Over 400 scientists from 25 institutions. They used a powerful camera in Chile to map hundreds of millions of galaxies. These aren't competitions. They're coalitions. The data is just too vast. The challenge is too profound. No single country, no one team could solve it alone. What drives all of this is a shared commitment to a process. Open data sharing, rigorous peer review. When a space telescope makes an observation, that data often goes into a public archive, available to any researcher, anywhere. A graduate student in India can analyze the same cosmic light as a professor in California. Ideas get published. Then they face the scrutiny of the entire scientific community. The process is slow, it can be contentious, but that's how error gets filtered out, how truth gets refined gradually. It shows science not as a set of cold facts, but as a conversation. A living, self-correcting conversation among people. This collective project, It means the mystery of gravity belongs to everyone. It's a shared puzzle for our whole civilization. A question we're all working to answer together. We look up at the same stars from different corners of the same planet, and we're united by that wonder. The quest to understand the force that shapes the cosmos in the end. That's a profound expression of what it means to be human, to look beyond our borders. Geographic borders, intellectual borders, and to seek our place in the grand story of everything. There's a real beauty in not knowing, to be under a starry sky, to feel that silence, and to realize the rules behind those lights are still a mystery. That's not a failure, it's an invitation. Science at its best isn't just a list of facts, it's a romance, a love affair with what we don't know. It starts with awe, that child's question looking at the Milky Way. What is that? How does it work? The equations, the telescopes, the years of work. They all come from that first spark of wonder. Carl Sagan said it, he said, "Somewhere, something incredible is waiting to be known." That anticipation, the universe holding its breath, ready to show a secret, that's what drives discovery. It's what gets a researcher up to check a detector. It's what keeps an astronomer at a telescope all night. It's knowing we're part of a story so much bigger. A story whose next chapter isn't written yet. So when we face these deep space anomalies, when we consider that gravity might not be what we thought, we should pause. Not in frustration, in appreciation. This mystery is a gift. The universe reminding us it's stranger, more complex, more wonderful than we can imagine. It keeps the cosmos from becoming ordinary. It means when we look up, we're not just seeing points of light. We're seeing a question. And in that question is all the beauty of being alive right now, able to ask it. The search for answers is noble, but the state of not knowing, standing at the edge of a vast, uncharted truth that's sublime. It connects the intellectual pursuit to something deeper. An almost spiritual sense of the grand, mysterious tapestry of existence. The cosmos should look the same in every direction. That's the assumption, the cosmological principle. On the largest scales, the universe is supposed to be smooth, a uniform soup, no center, no edge, no place that's special, but then you have to ask, what if our place is special? The evidence is pointing to that. We might be inside a cosmic void, a bubble of emptiness, hundreds of millions of light years wide. They call it the KBC void. In this region, the density of galaxies of matter is lower, much lower than the average. It's like we're in a clearing, a vast spherical clearing in the cosmic forest. And this isn't just a local curiosity. It could explain the tension, the Hubble constant discrepancy. If we're in an underdense region, the local gravity is weaker. Space here expands a bit faster. Our local measurements would give a higher expansion rate, but observations of the early universe, they average over everything. They'd give the lower, true average rate. So the void could be the reason the numbers don't match. It means we're not measuring it wrong. We're just measuring from a privileged point. An unusually empty point. But there's more, another anomaly in the motion of the largest structures. Galaxy clusters, they're drifting, not just with the expansion but together. A coherent flow, a dark flow, as if something immense beyond our observable universe is pulling on everything. Something from before our Big Bang, maybe. Or from a neighboring universe. It sounds like fiction, but it's from the data. The dark flow means the universe isn't isotropic. There's a preferred direction. A current in space-time. So the KBC void and the dark flow together, they challenge the cosmological principle. They suggest the universe is lumpier, more textured, influenced by things we can't see. For gravity, the implications are deep. If these structures are real, then gravity's role is more complex. Forming such vast underdensities, such coordinated flows, it might require a tweak to how gravity works on these scales. Or it might mean dark energy isn't uniform, that its strength varies from place to place, tied to the density of the cosmic web. It leaves you with a thought. Our entire observable universe, all 93 billion light-years of it, might just be one neighborhood, one sample, and it might not be a representative sample. So understanding gravity becomes about understanding our place in a cosmos whose full structure is still hidden. You don't need a degree to look for answers. If you're curious and you're online, you can be part of it. This is Citizen Science Now. Thousands of people just watching things, helping to solve these big questions. There's a project called Galaxy Zoo. It started because computers had trouble with something basic, sorting millions of galaxies by their shape. Is it a spiral? Is it elliptical? Are the arms tight or loose? Those shapes tell you the galaxy's history. They show how dark matter worked on it. They hint at the rules of gravity itself. So the astronomers asked the public. They put the pictures online and asked for help. The response was huge. Millions of classifications, from volunteers everywhere in their homes on their breaks. That human ability to recognize patterns, to see shapes and differences, it made a map. A detailed catalog of everything out there that no algorithm could ever produce. And that data has led to discoveries, strange green P galaxies, rare galactic collisions, all spotted by volunteers, and it's not just clicking. Amateur astronomers with their own telescopes contribute too. They watch variable stars, stars that brighten and dim on a schedule. That rhythm helps measure distances in space. They track asteroids near Earth, pinning down orbits, which helps protect the planet. This isn't just a pastime, it's a distributed sensor network. A global community putting pieces into the puzzle. Every data point, whether it's from an observatory or from someone's backyard, it makes the map of the cosmos more complete. This public role goes further into support. Big telescopes, space probes, underground labs, they're funded by public money. They're a collective project. A way of saying that understanding the universe matters. When you engage with the science, when you feel that wonder and you advocate for the search, you become a stakeholder. You're part of the extended team, and that changes everything. It turns the whole thing from a lecture into a conversation. It gives you agency. You're not just watching a mystery get solved. You can help sort the clues. If you build your scientific literacy, if you ask questions and find good sources, you join the community pushing at the edges of what we know. The next big anomaly, the clue that unravels dark matter or changes how we see gravity, might be seen first by someone who just decided to look a little closer. At the sky, or at a screen full of faraway stars, the universe's biggest mysteries are out there, and they're asking everyone to join the search. The purest questions can build the most practical bridges. Physicists are chasing gravity across the cosmos, and they're also, quietly, building a better world. The instruments from that quest become the tools we use later. To test if gravity changes by a billionth of a percent, you need clocks of incredible precision. That drive gave us atomic clocks, and those clocks now form the heart of GPS. Every map on your phone, every navigation signal, depends on that timing. It came from testing relativity. To listen for ripples from colliding black holes, they built LIGO. A laser interferometer so sensitive it can measure a disturbance 10,000 times smaller than a proton. The laser tech, the vibration control from that cosmic listening device, it's now refining how we detect early-stage cancers. How we image the human body with new clarity. The pattern is deep. The World Wide Web was invented at CERN. That's a particle physics lab. They didn't set out to create a global network. They needed to help physicists share data about the building blocks of matter. That tool for curiosity reshaped everything. It's the same with gravity. The need to track spacecraft like the Pioneers with absolute precision pushed the development of the Deep Space Network. Giant radio antennas. That system now supports all interplanetary communication. And the algorithms made to filter cosmic noise from telescope data. They're the ancestors of the image processing software in modern medical scans. This is the hidden engine of fundamental science. We look up at the stars and ask why. And in building better eyes to see, we invent new ways to see each other, to see our world. Investing in the search for dark matter or a new theory of gravity, it's not just an investment in abstract knowledge. It's an investment in a pipeline. The next generation of atomic clocks might enable flawless autonomous vehicles. The next leap in satellite tech, driven by the need for more precise gravitational maps, it could revolutionize global internet access. Or climate monitoring. The technological landscape of the next century is being seeded right now, in underground labs, at telescope control rooms, in the equations of theorists grappling with the force that holds the universe together. The quest to understand gravity is a dual journey, outward into the cosmos and inward into the fabric of our own future. The pursuit of truth has a weight to it, a responsibility. When you're rewriting the fundamental rules of the cosmos, how you share that discovery matters. It matters as much as the discovery itself. We live in an age where information moves at light speed, but understanding lags behind. A complex finding about gravity can be stripped of its nuance, turned into a headline, twisted to fit a narrative it was never meant to serve. This places an ethical duty on the scientists at the forefront. Their challenge is to communicate with radical clarity, to explain what they know, what they suspect, and what remains unknown, without letting excitement tip into exaggeration. It's about building trust through transparency, ensuring the public's sense of wonder is met with intellectual honesty, not mystery for its own sake. This stewardship of knowledge is a guardrail against misinformation, anchoring a disorienting shift in the solid ground of verified evidence. And that leads to a deeper question about the knowledge itself. If we confirm one day that gravity is not a fundamental force, that it's an emergent illusion, a side effect of quantum information, what does that mean for our relationship with the universe? It's a staggering leap. History teaches us that profound understanding often precedes profound application, in ways the original discoverers never envisioned. The scientists unlocking the secrets of the atom. In the early 20th century, they could not have foreseen nuclear energy or medicine. They were chasing a fundamental truth about matter. So we have to ponder, with humility, the long arc of this gravity research. Could a complete theory of quantum gravity, centuries from now, suggest new principles? Principles that might one day inform technologies we can't yet dream of. Related to energy, or space-time, or propulsion, the possibility is speculative, but it underscores a timeless theme. With great knowledge comes not just power, but the imperative to wield that power wisely. This ethical dimension circles back to the core motivation for the search. The primary imperative is not control. It's understanding. It's the honest, open, collaborative pursuit of truth, for the betterment of all humanity. The goal is to align the journey of discovery with our shared values. Curiosity, integrity, a commitment to using knowledge to illuminate, not to obscure. To solve the mystery of gravity is to solve a piece of our own story. To find a deeper coherence in the cosmos. That pursuit, conducted with responsibility and wonder, ensures something. As we reach for the stars conceptually, we keep our feet planted in the shared ground of our humanity. The greatest discovery isn't just a new equation. It's the wisdom to know what it means for us all. The pieces are scattered. A galaxy spins too fast. A spacecraft drifts. The cosmos accelerates, and two measurements of the universe's expansion don't agree. Each one is a riddle. Together, they form a pattern. And the pattern says our gravitational framework is incomplete. It's a magnificent approximation. It works perfectly in our solar system, but it begins to fray at the edges. The universe is sending a message, not one loud shout, but a chorus of quiet whispers, from every scale of reality. No single theory explains all the whispers. Dark matter handles the cosmic web. It handles gravitational lensing, but it stumbles on the details inside galaxies, and it offers no clear solution for the Pioneer drift. Modified Newtonian dynamics solves the galaxy rotation problem. It does that with grace, but it struggles with galaxy clusters. It can't account for their fierce gravity without invoking its own form of unseen mass. Then there's the Hubble tension and cosmic acceleration. These are monumental challenges to any simple story. This isn't failure, it's a rich mystery. The truth likely isn't about choosing one existing path. It's about forging a new one that incorporates all this contradictory evidence. This is where the creative work is happening. Scientists are trying to synthesize the clues, to build a bridge from many puzzling pieces to a single, elegant understanding. One idea that emerges is a chameleon theory of gravity. Imagine if gravity's strength wasn't a constant. Imagine if it could change based on its environment. In the dense neighborhood of our solar system, with planets and abundant matter, gravity would act exactly as Einstein predicted. It would blend in, it would match all our precise tests, but in the vast, near-empty deserts between galaxies where matter is sparse, the rules would shift. The force would become a little stronger at these immense distances. That could provide the extra pull for fast-orbiting stars, without invisible matter. It could even alter the large-scale dynamics of the cosmos, influence the expansion rate. This chameleon behavior offers a possibility. It could address solar system precision and galactic-scale anomalies. In one framework, the Pioneer Anomaly, the Fly-By anomalies, might be traces of a transition zone, where the density of matter falls just enough for gravity's hidden character to begin to show. The differing measurements of cosmic expansion could reflect our position in a universe where gravity's effects aren't uniform. They're subtly textured by the distribution of matter itself. This is still speculative, but it represents the next step. It moves beyond defending one hypothesis. It asks how the full spectrum of evidence can be woven into a coherent new picture. Of nature's most familiar force, the work is to listen to the entire chorus of whispers and to discern the one song they are all trying to sing. The next decade is going to be pivotal. We're entering a period where questions that have lasted a century might finally get their answers. The data is starting to come in. The Euclid Space Telescope is already working, looking out into the dark sky. Over the next several years, it's going to build a three-dimensional map. A map of billions of galaxies, covering 10 billion years of cosmic history. And this isn't just a picture. It's more like a forensic scan of the invisible universe. By seeing how these galaxies cluster and how their light gets bent by mass we can't see, Euclid will weigh dark matter. It'll do that with a precision we haven't had before. It will measure the push of dark energy across cosmic time. The map it makes will be our most detailed chart yet of the territory we're trying to understand. Any theory of gravity, any model of dark matter, will have to account for every single feature on that map. At the same time, a new window is opening. Gravitational wave astronomy. Observatories like LIGO and Virgo have already heard collisions. Black holes, neutron stars. The next generation of detectors, the ones planned for space, they'll listen for a deeper hum. The background rumble from the universe's first moments, a signal from the violent birth of spacetime itself. If they succeed, it would be like hearing an echo of creation. That primordial vibration could carry imprints of physics from energies we can never recreate. It might show if gravity behaved differently back then, in that seething infancy. Or if new particles, exotic ones, played a role in shaping everything. On Earth, the silent watch continues. Laboratories buried deep under mountains keep listening for the faint bump of a dark matter particle. But the search is broadening. Precision experiments are now testing for deviations in gravity, but at microscopic scales. They're looking for hints of a fifth force that only operates over tiny distances. Or for subtle violations of the equivalence principle, the idea that all objects fall at the same rate. These tabletop experiments, they probe the frontier. The place where gravity meets quantum mechanics. A positive signal here would be as revolutionary as any telescope image. It would mean gravity's rules aren't just cosmic. They're woven into the quantum fabric of reality. The scientific community has a hopeful anticipation. We're not waiting for one single answer. We're waiting for a constellation of clues to align. The data from Euclid might show that dark matter halos have a specific substructure, one that matches simulations perfectly. That would be a powerful endorsement. Or it might reveal that galaxy shapes and rotations follow simpler predictions, the predictions of a modified gravity law, with a consistency you can't ignore. A gravitational wave observatory might detect a pattern that only makes sense if dark energy has a dynamic, changing nature. Or a lab might measure a force that doesn't fit the standard model. The hopeful breakthrough is a smoking gun, a piece of evidence so clear, so compelling, that it points decisively down one path, toward a universe filled with unseen particles, or toward a fundamental rewrite of Einstein's equations, or, most excitingly, toward a third option, one we haven't even conceived of yet. This decade offers our best chance to find it. We're living through a period that future textbooks might describe as the turning point, the moment when the veil over one of nature's deepest secrets began to lift. Not with a shout, but with the steady, accumulating light of data. The cosmos has held this mystery for billions of years. We get to be the generation that finally learns to listen. The final frontier isn't just a place, it's a state of mind. You stand here on this tiny world, and you look out at a cosmos that doesn't follow our neatest rules. It reminds you of something. We are not the masters of this universe, we are its students. And the lesson it's teaching us through every spinning galaxy, through every drifting probe, is one of beautiful incompleteness. These anomalies aren't failures of our science. They are its greatest successes. They are evidence that our methods work, that we've looked closely enough, measured precisely enough, to find where our best ideas meet their limits. The strange rotation of galaxies, the quiet tug on distant spacecraft, the universe accelerating away, each one is a cosmic signpost, a marker on a map that says the territory ahead is uncharted. We started with a simple force, an apple falling in a garden. We built that into a geometric masterpiece, a theory that could bend starlight and describe black holes. And now we find that even that masterpiece is a sketch, a brilliant, powerful approximation of a truth that's stranger than we ever conceived. Whether dark matter or modified gravity will win out, that question is less important than the fact we're asking it at all. That we've reached a point where the foundations of reality are up for debate. This is physics in its most vital form. It's not a dusty collection of facts in a textbook. It's a living, breathing conversation, a global community of thinkers and observers piecing together a puzzle whose final shape we can't yet see. The universe is speaking. It speaks in the language of mathematics, written in the light of distant stars and the silent drift of empty space. We are only just beginning to decipher its grammar. So as we return from the edges of the cosmos, we carry back not a final answer, but a renewed sense of wonder. The journey itself is the destination. The process of questioning, testing, rebuilding our understanding, that is the adventure. It connects the curiosity of a child gazing at the Milky Way to the equations of a theorist. It ties our place on this pale blue dot to the vast, mysterious forces that sculpt the cosmos. What do you think lies beyond the signposts? Does the path of unseen matter feel more compelling? Or does the elegance of a rewritten law, a subtle shift in the rules, resonate more deeply? The conversation continues. Your perspective is a part of it. Share your thoughts. And if you want to follow this story as it unfolds, as new telescopes peer deeper and new ideas take shape, subscribe to join us. The next chapter of this cosmic mystery is being written right now, in data and in dreams, and we all get to be a part of it.